Hello community. Let's talk how we can optimize our smaller language model with a high order cognitive reasoning pattern. Now, currently when we do in-context learning, we feed multiple, maybe up to 100 single examples here into the prompt engineering, and then we expect that the machine is able to deduct here a general pattern. However, what do you think about if we change our approach and we feed into our ICL prompt engineering task here an abstract reasoning pattern and let the machine learn on this, what we expect now. Now, part 1, beautiful, and now welcome to part 2 of this video. Now, I was motivated by this idea, in mathematics we have general solution. So for all available potential quadratic equations that we have, we just provide it here with the generic form that can solve every quadratic equation. Now, what we do currently in the training data set of the pre-training, the fine-tuning, and the reinforcement learning, we provide thousands and thousands of single examples. So maybe, and especially here for the smaller language model, we should say, hey, it's time to change. Let's think about what we could do. Can we go a similar path like here in mathematics, where we find here an abstract higher level solution to all possible type 1 problems? In part 1 of this video, remember we talked about here the pre-trained policy language model, the pi theta, especially when we have a complex problem solving that can be framed as a multi-step reasoning process. And we were talking here about the model output distribution pi theta and how we can use here the policy optimization framework. And I told you if we use this here in combination here with the partially observable Markov decision process, where we know how to handle this on a mathematical basis here, the combination of those two will guide us here into the future, into the next step of applications. So what I want to show you here today is we will shift from an ICL-based example-dependent reasoning to a higher level automated reasoning paradigm. And note that this is not just at a higher level reasoning abstraction that we are looking for, but we want to automate this because there could be quite a lot of theoretical problems here in the human civilization. So, great, sounds like an interesting task. Let's start. So this new framework incorporates now abstract cognitive reasoning patterns rather than specific examples in our in-context learning prompt. So, you might say, great, so human civilization, how many cognitive reasoning patterns do we need here to provide here a basic functionality for the human civilization? Now, easy. Traditional ICL, we rely here on high quality, manually, humanly crafted, domain-specific examples. The synthetic datasets do not perform as well as we hoped for. And now we just transcend here this dependency by focusing here more on these abstract cognitive patterns that are now specific for each problem characteristics, rather than just providing here specific examples that we just can copy from the internet. So we are now faced with the problem, if we have specific characteristics that we have to solve, we have to have a seed set, and then we start to try to find here the optimal configuration for an automatization here of here the best optimal path. So I just went here to ChatGPT and said, hey, how many do we need? And ChatGPT came back, there's always an answer if you ask it, and says, hey, the human civilization likely requires 20 to 50 foundational reasoning patterns to cover the spectrum of logical, ethical, creative, and adaptive challenges in the human society. These patterns are flexible, combined, adapted, giving rise to thousands of some nuanced reasoning strategy specifically tailored to your domain or your problem. So I said, okay, I go with 20. And I said, hey, just list it. And then you have here GPT, deductive reasoning, inductive reasoning, causal reasoning, reasoning by analogy, heuristic reasoning, divide and conquer, system thinking, game theoretical reasoning. And I said, hey, we can further abstract this away. And after some discussion with my little AI system, ChatGPT came up and we had here a final set of abstract categories of this 20 minimum set here, and we have 6 elements. We go for analytical reasoning, so the logical causal analysis, the relational reasoning, So for the connections and whatever happens here in the dependencies, the problem decomposition to break down a real complex task here into smaller subtasks and solving this. Then the systemic reasoning, understanding here the complex interconnect to the environment. Then the ethical and the social reasoning, this thing with what the humans do here, this value-driven decision depending on what you believe in. And then we have something like a creative reasoning and exploratory, so whatever goes here into new discovery, innovation, this stuff here. So, and with this 6 abstraction ideas here by ChatGPT, I was quite satisfied. Now, we're going to look at a new research publication in about 5 minutes, but they also came up with the idea of 5 reasoning elements. And those are their 5 reasoning elements. They go with a system analysis, a one-step thought process, a chain of thought that we know, then the divide and conquer idea, and a self-reflection and refinement. And I ask here my AI system, hey, can we find here our 6 elements and their 5 elements? It's actually quite easy because their system analysis we can integrate here under system reasoning and analytical reasoning. The one-step thought process is simply here problem decomposition, also going with analytical reasoning. Chain of thought is here relational reasoning and problem decomposition. Divide and conquer, problem decomposition. And then everything that is connected with self-reflection goes in explanatory and creative reasoning. And maybe you also have a part here in ethical reasoning, So I think we are quite set here on our minimum set here of 5 or 6 atomic reasoning elements. If you want to compare this to our original 20, but always under the condition that here ChatGPT made no mistake, and this is all we need in a human civilization. Great. I asked ChatGPT to analyze it a little bit further, and after some minutes we arrived at this. This framework now kind of is a coherent framework if we look at it in a loop structure. So if we look here at the cyclical reasoning loop, then can ensure kind of a balance between exploration, validation, exploitation, and execution. Why? Our first identifies here the problem context, then we incrementally analyze it, and we organize here then the next step here into a coherent chain with clear dependencies. Then we try to handle the emerging complexity by having here multiple modules, creating here multiple modules here in this linear process chain. And then we have we refine the system, we'll validate here the reasoning arguments, and we have a feedback loop here for self-improvement. And yes, I know what you're thinking. You're thinking here Monte Carlo tree search algorithm here for exactly this. And what a coincidence that I tried to find this approach that will lead us automatically here into our MCTS. If you want to have a mathematical perspective on this, I just ask, hey, can we find also a coherence to a more strict system? And I was talking about completeness, adaptability, scalability, efficiency, and this, this human component, this human-centric design. And yeah, after some discussion, ChatGPT kind of agreed with me here, that with completeness covers here all the essential phases of reasoning, understanding, progression, structuring, simplification, validation. So you see, we are building here a simplified version. Great. And then, of course, there's the critical question, hey, do we miss anything if we do this? Yeah. And after some discussion, ChatGPT came back to me and said, there could be a lack of emphasis here on this creativity or this divergent thinking. Everything is so linear logic here. So if you have here higher novel problems, then this creativity approach or here, this highly divergent thinking, this just going crazy for a minute and try where we can go, this might be here a good add-on that we should keep in mind. However, looking back now, the conclusion that I found with my GPT system is quite nice, no? Because if we go with 5 or 6 atomic reasoning elements here, we find if we design it in the right way, they are coherent, they're interdependent, and they kind of form a cyclical, scalable framework. And this is exactly what we need as a base here for our higher level abstraction here for the cognitive pathfinding. They more or less cover all the critical reasoning criteria, including what we humans call understanding, progression, structuring, simplification, and validation. And ChatGPT at least thinks there are no significant gaps. There's nothing like a human feeling or human love or human emotions, human happiness. Oh, come on, this is not a logical structure. So this coherence here ensures that they work synergistically as a comprehensive paradigm, I love this wording, for reasoning in complex problem-solving context. No? And you see, in this simply 5-minute journey, I brought you now to a particular point in time where some new roads open up to us. No? But just to make self-reflection, we have to make sure that we are not going somewhere crazy. I said, but why did not Nietzsche or Kant, as a modern philosopher, discover this simple pattern to explain here the complete human world and the human thinking process? And ChatGPT always has an answer. There's no problem, it can't answer. And said, yeah, okay, so if they focus on metaphysical and ethical frameworks here, Kant, for example, here the foundation of knowledge and morality, or Nietzsche here the critique of culture, values, and human nature. And we went on, and then we found something that I think is interesting. Trying to find here a mapping between those two worlds, there was suddenly this chapter on philosophical complexity versus functional simplicity in computer science. So, ChatGPT at least says that the atomic reasoning elements that we found here, while elegant and systematic, aim to simplify the reasoning process here for a practical computer science application if we want to run a small language model and increase here the capability to solve more complex problems. Well, of course, this is my task here. And then, philosophers like Nietzsche and Kant were concerned with the interplay of ideas, emotion, and existential conditions. And the 5 elements abstract away from these nuances, focusing purely on the mechanics of reasoning rather than the full scope of human experience. I'm okay with this. Just focus here on the mechanics of improving the system performance. That is great. But then, if I look deeper, that was interesting because Kant, with the emphasis on structuring thought and categories of understanding, this kind of resonates here with our system analysis if you have a very wide interpretation of this. And Nietzsche here, his focus here on reflection and critique here aligns here, if you want, with self-reflection and refinement. And then Friedrich Hegel, in seiner dialektischen Methode of Thesis, Antithesis und Synthesis here, he reflects here on the aspect of divide and conquer and this chain of thought idea. If you want, you can interpret this here, if you want here, into this framework. So we are not completely off the road. We are not completely going crazy here with this. Great. And then, I already mentioned this here, this Monte Carlo tree search. Having all these possibilities in finding here the best reasoning path, what search modality, what search algorithm do we use to find the best path in this vast mathematical space here? Maybe we build a specific vector space for this. So searching here for the best causal reasoning path. So idea, simply we use here our tools from Monte Carlo tree search for searching here a vectorized or a discrete search space to solve here this particular problem of finding here the best solution in a higher level abstraction. Let's do this. Yeah, if you want, I have here a side step where I show here how this 5 atomic reasoning action could be further integrated here with Monte Carlo tree search for the tree initialization here and the contextualization here of our Monte Carlo tree. If you want to have a look at this, beautiful, but just the overall picture, Normally we have here Monte Carlo tree search if we have more or less discrete problems, but if we vectorize here the search space, we could have a continuous search, we can have some guided rollouts, and then we have, as you know, there's some beautiful metrics that allow us here to find the close by or nearby neighbors here for particular topics. Cosine similarity is one of the tools we can use. So use exactly where I'm moving for. So if we go now a step further in my discussion and we are looking for an enhanced Monte Carlo tree search that is particularly well suited here for our 5 atomic reasoning elements, you just can do a play if you want with your AI system. And I was talking here with my machine more than 3.5 hours in total about the refinements about this. No? And for the structured initialization, incorporate domain-specific knowledge to initialize here the tree structure on your particular domain, on your constraints here in an intelligent way. Multi-level expansion, multi-reward models that you know already. We have multiple videos on this. And then, yeah, you have, if you have a specific embedding mechanism, you can try to use here a particular polarization that you say, here I have a particular emphasis here on the cognitive complexity of a node that I don't want to build. But this is about the code implementation already. So why is it kind of a nice way here, MCTS here for vectorized search spaces here, we have a balance of this beautiful exploration and exploitation phase. So this is more or less ideal if you want for requiring creative and iterative reasoning. Iterative reasoning is our chain of thought, and this creative is for more complex topics. We have a beautiful scalability, and we have a feedback loop backpropagation from the classical Monte Carlo tree search algorithm. So what we do now, if we have this search algorithm and we have our mathematical vector space, let's say, or you have a discrete space, where you are trying out a different reasoning path, given here a seed data set, and you have to allow the system to learn on this new methodology. So you have your 5, or whatever you define, reasoning actions here, and they act here as the fundamental building blocks for the reasoning path itself. And then you construct here the Monte Carlo tree search algorithm. And then what you find that if you expand it and whatever happens here, you come to solutions. And then each problem, if you want, is then framed as a tree search, where Monte Carlo tree search identifies here the optimal path. And then this path here, this path gives us multiple possibilities to go on. The authors of a paper I'm going to show you said, okay, this is it. We found here an augmentation path, a solution path, and we take this path. So they say our paths are distilled into some abstract reasoning templates, like we know from, I don't know, whatever, based here on the computational efficiency and effectiveness, and I'll show you here the code in a second. And then we store those templates here as kind of, they call it a sort card, or a solution card for a complex problem. You know, this is exactly what, like we started this video, we want to find a generic solution form for solving quadratic equations. Now, our, if you want, problem is not a simple mathematical formula, but it is a more human-like path of finding solution, like we humans do, and we find solution to all our problems that we currently post on the internet. Beautiful. So what the authors of the study did, they said, great, when we have here the Monte Carlo tree search now finished after some period of time, after some cost that you say this is my limit, and, we have now the best possible reasoning path, and we write it down here in a reasoning template, and we call this template a sort card. And here you have a sort card, so for one specific problem characteristic, you have the solution. Okay, let's come back to the human mind, and these are some of my thoughts. I have no copy here of screenshots here of ChatGPT or whatever. Think about the Monte Carlo tree search. So each node that we build here in this search represent here a partial reasoning state, and expansion correspond here to generate possible next reasoning steps, or what we call actions, especially in the MAL continuum. So the process continues until reaching here a terminal node, either by hitting a maximum depth. After 7 steps, you stop, or you identify here a conclusive answer, after which standard MCTS backpropagation update now the nodes, visit counts, and value estimates. Great, we have this feedback loop in the backpropagation. And if repeated sampling of the same state produces here some stable outcomes, we know, hey, we found a solution to our problem, and the algorithm concludes that the solution is accurate and can stop expanding further here in our virtual tree structure. Great. Now, examples are over nice, so let's do a simplest example of running here Monte Carlo tree search to explore multiple reasoning paths. We start with a root node. In the root node, I define here the problem. What is the square of the number 12? Yes, I know it's simple, but just about the procedure. So from the root node, we need to pick an action to expand here the root node into further child nodes. If we have multiple nodes, you can say, okay, I have to define what is the meaning of square in a mathematical operation. You can ask, hey, is the number 12 in any way particular? Should I know about it? Or whatever you want. You have multiple paths, you explore multiple paths. Each path now, each reasoning path now gets here a quality value, a Q value, a reward for correctness, given its specific correctness, which is easy in a mathematical operation, square 12. And we already have a known length in our tree search path that we went. And let's say this is simply somehow corresponding to the cost, to the compute cost. So, and now by applying here a value of computation, this VOC inspired score, the algorithm selects now a particular path that best balances now the correctness and the complexity of, you want, the cost of this particular search algorithm. And then this chosen path becomes now a reusable high-level reasoning template for future problem, become also kind of a minimal set of a valid reasoning path for a particular complexity. Let's formulate it in this way. And now I had a simple question, because if we go this far, you know what's going to happen now. No? So given a multitude of reasoning path solution cards, could now an AI be used to condense them any further to a minimal atomic set of logic operation to build up any combination of this reasoning path? Let's say we are talking about physics or chemistry or medicine. So what I'm looking for is kind of a generative functional here for a causal reasoning operation in a particular mathematical space to simply improve here the AI reasoning capabilities. And you know, I'm looking here especially here for a small language model, and I'm looking, if you want, here for the logic primitives here in this particular code implementation. So to understand this further, I'm currently running the test, and maybe in one of my next videos I will tell you the result if I find any. We are here focusing on, if you want, the automation process of building up reasoning processes from our seed datasets. So we start with some simple mathematical operation, and then maybe we have some physical operation, and then we go into some human logical operation, and then we go into financial operation, and you get the idea. So short summary, so after executing here all our different Monte Carlo tree search path here on the seed question, that we initiate the system to come up here with the first solution, the algorithm selects here an optimal reasoning trajectory per question by computing here our value of computation inspired score. And the score, as I told you, balances here the reward. So this means here the quality value of this particular node that we can define in different categories against the simple computational cost. One indicator might be a path length, or you can add your parameters to this, and therefore you can identify here the single best reasoning path to solve here a higher level abstraction. Great. And then these selected reasoning paths are then abstracted and distilled into the sort cards. And then those sort cards serve here as a high-level solution template that encode here a structured, verified reasoning strategy. Now, the authors of the study I'm going to show you in a minute, they did this here and said, okay, this is our written down solution path. Or as I have shown you here in the beginning of my video, I was operating here in a more abstract mathematical space of, I don't know, 1,000 plus dimensions. And I leave here the complexity of the high level abstraction template in the complex mathematical space, and I operate here, if you want, in a vector store, in a vector space with those sort templates, and I don't break it down, and I do not encode it, or I simplified it into a human language, but I leave it here living in their original higher mathematical, let's say, vector space, for example, but different methodologies. So you know that I'm looking here for a smarter small language model. I don't want to pay the price to those global corporations. So what we have here a pre-trained small language model, great. And then if we do all of this, what we just talked about, we can find here our, if you want, template structure, our sort card, our solution card, our instruction here that we have now to follow, not on an example based, but on a higher level abstraction level. Great. So optimal reasoning path are described here on a higher level abstraction. And this is, if you want, encoded on these sort cards. Encoded, if you want, in the human language or as a mathematical, whatever you use, go with whatever fits your particular domain. And then we have inference. And then we have the actual query that comes along. No? And what I'm hoping now that if we have here this new learning methodology, that we can use this distilled reasoning patterns here in our little cards at the inference time for new unseen test problems. So we just have to verify, does it work? And the beauty is now, we move to an abstraction level that is much simpler because I'm looking here for a small language model. So I don't need here, hundreds of billions of retrainable parameters in the model, but maybe I can do it, with 30 billion retrainable parameter if I focus the system to learn here this higher level abstraction and not provide it in with 10,000 examples of individual quadratic equations, for example, or simple human patterns in documentation. Now, having hundreds of videos on lower and parameter efficient fine-tuning and adapter tuning and whatever, the next logical step is if we train this, and let's say we train this here in a particular domain, we can build an adapter of this and we have the complete software algorithm, everything available for us. But this is now a higher level abstraction adapter that is able to solve here particular problems that we trained it on. Great. Yeah, of course, we have to pre-compute this, if you want, adapter level, and abstracting here our valid reasoning strategies. We have to verify them. I will show you in a minute what our validation metric structures will be, but clear. Validation. Okay, so the authors of the study go here with a cognitive complexity framework and they try to come up with 3 different metric systems. So, what is the simplest you can think of? Simply of the number of sub-problems that we are trying to solve. If you have real complex tasks and we decompose the task into simpler subtasks, how many of these subtasks do we have? 2 or 412? Then we have kind of a problem condition complexity. This tries to assess here the complexity of the problem constraints. How high is it in general? And then we have here the semantic similarity. And this is what you already know here from simple sentence transformer system, BERT systems. We simply evaluate here with, for example, cosine similarity, the closeness in our vector space here between a target problem and the known example to solve here our known example on a higher abstraction level. And then you can use these metrics to categorize and retrieve and whatever you want to do with your sort cards and find the perfect sort card for a given unseen test problem. So select the reasoning pattern. So for each new test problem that we feed in, the system calculates now the cognitive complexity using here these 3 parameters, and then it tries here to match here a particular sort card that was an automated learning process by the small language model itself. Let's say we extract 2, 3, 4, 5 of these possible solution paths based on these scorecards. And we do not have to provide hundreds of in-context learning examples because with an abstraction logic, we are able to find here a generic pattern in all of this. Yeah, if you want to go here how to compute a semantic similarity, I use, as I told you, simple a BERT system here that is publicly available. Or if you want to compute the sub-question count, the simplest way you can do, for example, is with Spacey. This is all open source. But you know what is really nice if you think about this? That this framework provides here a way to generalize here the reasoning across multiple domains. Think about it. We can have an adapter for mathematical complexity, for some human common sense, whatever this means, and a more scientific-oriented reasoning patterns that we have to pre-trained on. And we do not need here pure models or small language models that are really domain-specifically fine-tuned here. We can have this here with this new approach of abstraction. So this means let's have a multi-cross-disciplinary problem. I can just put on here the, if you want, or attach here the chemistry, abstraction, adapters, and the physics trained adapters, and I have generic solution in those adapters that I can use in combination, and I don't have to do any additional pre-training of my small language model. So this ICL-based methodology, and I've shown you that ICL was already talked about to substitute at least the fine-tuning. This now really would work great here on a pre-trained small language model if I have a given complexity and a given abstraction where I know the path to solve given problems. But of course, this should be a self-learning system, no? So complexities will evolve with time or with higher complexity given the task. So should my, if you want, high-level abstract reasoning system also adapt here to an increased complexity? And I think yes. So this system should be able to assess, select, and adapt here multiple solution cards, or if you want here a specific selection here for novel challenges or maybe novel combination of challenges. And yes, in my demos, I work here in the science domain. So this is also another reason why I leave here, if you want, my solution cards or the best optimal path here in a vector space. And currently, as I'm recording this, there are some demonstration runs. I just want to find out, can I put here the complete reasoning path and embed it in a vector? Or do I need to subdivide here the reasoning path in different vector structures? I don't know yet about the optimization. Hey, but why not subscribe, and maybe in a later video, if I find a solution, I can tell you about it. Now, I just want to be clear here that the authors, I'm going to show you the study. Gee, I haven't shown you the study yet. They use here the value of computation-inspired metric, and I already talked about this. Now, this or their particular approach was a really simple one. So they calculate here a particular scoring function, give them here the reward function, and they measure here the complexity or the cost here of finding here a particular reasoning path here simply by the number of actions or the number of steps taken. But I don't think that this, I mean, it's a beautiful start, gorgeous, but if you want to go into higher complexity, maybe the number of steps, if you operate already on a higher complexity manifold, is not really that criterion for you, but depending on your domain-specific problem. Yeah, I currently optimize here this parameter here. If you want to go here for this value of computation, if you say, hey, I don't really care about the cost, I just want to find here at least one generic solution to my financial problem, to my medical problem, to my whatever physical-chemical problem. Maybe you're not as cost sensitive because you want to find at least one generic solution that you can apply to your complete company. Yeah, this is the beautiful paper that reading this paper, I got so many new ideas, and I dared to not go their approach of the introduction. Please read it. You find a complete different approach to this paper here. Reading this is from November 27, 2024. The title is Beyond Examples, High-Level Automated Reasoning Paradigms in Context Learning via Monte Carlo Tree Search. Those are the authors of this beautiful paper. They are from the Department of Automation, Tsinghua University in Beijing, or the Beijing National Research Center for Information Science and Technology. Great paper. Let's just have a look at how they approach this. If you have here, yeah, they give you here the direct prompting. If you just think, hey, let's think step by step, and you don't provide examples here, real training examples that are specific, the system will tell you, hey, sorry, just thinking, telling me go step by step doesn't solve anything if you do not provide in-context learning a few short examples to me. If you do this then in the classical in-context learning, you provide here example 1, 2, or if you go here with many short examples, up to 100 examples, then this system can maybe deduct here a general path, or if you call, they call their solution high ARICL. If you follow their approach here with their simplification here in their VOC scores, then yes, they get here a beautiful explanation. If you want to see this in their visualization, this is the way to go. You have here their 5 atomic reasoning minimal set of actions. Then you have here the Monte Carlo tree search, where you have here this tree where all the different options are explored. Then you find particular pattern. This pattern you write down here in the sort cards. So you don't leave it there in a if you want continuous vector space, but you just write it down. Then you select particular source card for your problem, then you solve it, and you can have a verification run. And they, example, have the output reward model or the process reward model. They can calculate here exactly further parameters, but I'm just here exploring here new ways and maybe building on their system. I got so many new ideas, and maybe if you read this, you will get new ideas. Let's talk about their implementation and what they found in their performance data. And here you have it for all the different let's call it small models. 14b is not really a small model, but 7b is here a small language model. 6b, 8b, well, yeah. And so you see whatever they call ours is their particular implementation, but I think we can build on the implementation and improve significantly. But you see the indicators, if you compare this to a simple zero-shot chain of thought or a few-shot chain of thought examples, there is really a noticeable improvement even in their minimal improvement states. Great. So what they conclude, and this is from the paper, so by incorporating now abstract thinking patterns, and I think this is the beautiful idea we have been waiting for, especially for a small language model, rather than relying here on human intervention and human examples with a high quality, we are now focusing on abstract thinking patterns in the training data set and retrain our LLMs already on a higher complexity level. And yeah, we have to generate those levels, but therefore I showed you here the way how to automate the generation of those abstract thinking patterns. Now, two simple examples. If you're into physics, you know that Maxwell equation, the classical one, for electricity and magnetism, and everything that is connected with this. We found an higher level abstraction in these classical laws. So if you want, this is kind of an analogon if you're in theoretical physics, or if you then jump to quantum physics here, you have here the Lagrangian here of our QED, and you see it even gets more elegant if you develop here new mathematical notation for this. But anyway, I just wanted to show you with this generic formula, we can solve all individual partial problems that we encounter. And I think this is the beauty that we try to implement here, going now from example-based in-context learning here to a higher level abstraction in context learning. Or if you are into computer science and you have computational logic, mathematical logic, and complexity theory, there's also now the question, honestly, can we form here a logical formal perspective? Can we build here this foundation here for these atomic reasoning steps? So here, for example, some core logical connectivities and quantifier for this, or some inference rules, some causal modeling tools, some probabilistic updating mechanisms, and some basic abstractions. And we want to have here the minimum basis for the small language model for a strong, compact basis upon which we can build now this more complex, human-like reasoning structure in our small language model, and we can reconstruct this, and this will help our small language model to significantly improve their reasoning capabilities if we do this. But as I can assure you, it is not as easy to build this, and even if you use a different editors, the code generation is something that has not been done before, so you will run into limits if you have some automatic code editors, but never mind if you use Cursor or whatever, some bold new. There you have to invest a little bit in your own ideas to come to a conclusion. But I think, yeah, this is it for today. In context learnings, we are focusing now on the next logical step on higher order cognitive reasoning patterns that we integrate in our prompt. Therefore, we need a specific pre-trained small language model that is able to reason not on a specific example level, but on a higher abstraction level, a higher cognitive function that we try to implement here in our small language model. I hope you found it interesting. I have some brand new idea of my own I integrated based on this beautiful publication by our colleagues here in China. And I hope you enjoyed this video too. And if you liked it, why not subscribe? And it would be great to see you in my next video.